So this is a joint work at Middlesex University with Rajagopal Nagarajan and Florian Kambudo. So before I start, two caveats basically. So first is that this is very much work in progress. So it's something that we've been doing in our spare time up to now. So it's something that definitely has great potential, but at the moment it's not. It's sort of it's not quite what it could be yet. And finally, so the second caveat is that I'm not an expert on quantum anything basically. I'm a logician by trade, so I hope I've struck the right balance in not explaining too much and not explaining too little either. If I have, don't hesitate to interrupt me. So, very quick bit on theorem proving. So, interactive theorem proving, why do we want to do this? Automated reasoning is very nice. But you're always limited by the fact that when you do automated theorem proving, you basically your expressivity is always limited by whatever you can get a computer to prove for you. So when you do interactive theorem proving, you have much more expressivity because you can basically express a lot of stuff. Unfortunately, it does mean that you lose a lot of the automation. The interactive means that basically bits that the computer can't automatically prove you, and you have to do by hand. But you get a lot of mileage out of this because the more complex stuff, the tedious reasoning you can still do automatically, but the complex stuff is something that you can then express and improve things about. Your proofs obviously are still not be verified. So COC is the tool we use, the theorem prover. The particularity of this is that it uses constructive type theory, so the excluded middle is not in there. A proof is a construction, so you can actually turn your proof into executable code. You have a higher level of expressivity by dependent types. We'll see this in a moment. And yeah, the code extraction is definitely interesting because you can sort of turn the programs you prove properties of protocols into actual prototypes that it extracts to account. So the basis of this whole thing is the Curry-Howard paradigm. So basically, proofs are terms and propositions as types. So a proof is basically a program, a proposition is a type. So you might, for example, have a function from P to P which proves that so then x dot x of type P implies P. This is basically P implies itself. You might have a type. So this is the implementation of the OR. One of the left basically turns A into A or B. You've also got the right. But the main thing here is that basically proof checking is type checking, which is something that you can do automatically. The automated proof is type inference, so actually proving something is type inference, which is not decidable. The verification is automatic, type inference is not. So the formalization of quantum theory in COC is something that, so when we started out, you basically need complex numbers, you need vector, you need linear algebra, you need matrices. And when we started out, there wasn't really any library that provided both. This is always a problem with COC in specific. That you usually have a lot of libraries that do interesting stuff, but it's always very difficult to get them to work together. So we selected this point. We started using Korn, which is the constructive real number library, which is made in Nijmegen, which has complex numbers. It does a lot of fast arithmetic. It unfortunately doesn't do matrices, but it supports type classes, which is a sort of a lightweight module system that you can use to, we thought at the time, easily implement matrices. So that's we started out working this. The problem is that Korn isn't really, the ideal solution, even though it's a pretty interesting library. It seems to sort of development seems to have stopped lately. It's definitely been kept up to date. There hasn't really anything done over the last few years. There's little documentation, and it's constructive, and we'll see, so it's very constructive, and we'll see why this is a problem in the later on when I start showing some actual code. So we decided at this point to switch to another library, which is SSReflect. This is the library that Georges Gontier and his team have used to formalize the proof of the four-color theorem a few years ago, and now they've done the old-order theorem as well. I think SSReflect is basically well on its way to becoming the main linear algebra mathematics library in Coq. So let's look at some stuff. So the definition of a qubit. So here is where we see what dependent types are. So a qubit is basically a vector of 2 by n. Length of the vector is 1. So this is all the slightly strange notation is an artifact of Korn, because you're using real numbers rather than measurements. And what you see here is a dependent type is basically a type that contains a term. So in order to construct the value of a qubit, you need to provide a term, a proof of the fact that the length of this qubit is actually 1. So it's a dependent type. The type, it's not just a vector, it's a vector that depends on having this term. So it's a very nice way of combining proofs and types in. So if you have a type that has a certain property, that's basically the way to express that. Same thing goes for a gate. So a gate is a matrix that is unitary. You can then define a function applied that takes a qubit and a gate and a qubit and returns a qubit. And then, so the only thing is that now, and this Coq will do the administration for you automatically. The only thing is that you actually need to, so a function apply will need to construct a proof that if I take a qubit and a gate, this resulting thing is also a qubit. So the length of my vector basically is 1 as well. And obviously by proving by using the fact that the gate is a unitary matrix, it's pretty simple, but it's fairly well integrated into the system. So these are the basic definitions. This is all, by the way, still in Korn notation. This isn't using SSReflect, but the basic definitions, it's mostly a question of sort of changing the definitions. The basic stuff shouldn't change very much, so the expressions shouldn't change so much. So one of the things that you can do at this point is do the quantum coin flipping game. So the normal version is very easy. 1 coin, 2 players, P and Q, 3 turns, Q, then P, then Q. If the coin, the coin is heads in the end, P wins. If the coin tails, then Q wins. Each player can either flip the coin or not. None of the players can actually see the coin, and at this point it's fairly easy to see that there's no winning strategy because you don't know what the other player has been doing. So, yeah, you might by flipping the coin, you might as well worsen your situation out. However, if you do the quantum version of this, so quantum coin is just 1 qubit, 2 players again, 3 turns. In either of the classical states, P wins or Q wins. Each player can still either flip the coin or not. So flipping the coin is basically turning 0 into 1 and 1 into 0. But Q now has an additional option to apply the Hadamard gate to turn this into a quantum superposition. No one can still see the quantum coin, and now Q has a winning strategy, because if he turns it into a superposition, then whether, so if Q uses Hadamard twice, whatever P does, it will still be the same superposition, and then it will turn back. So in this case, Q is a winning strategy. So this is something that you can actually implement in Coq. So basically, you define types for a choice of P. So P can either do nothing or flip, N or X. Q, again, Q choice type for culture. So either we can do the two things that, so we can still do N or X, you can do nothing or flip, plus the Hadamard application, so Q choice. You define the game as basically something that takes choice of Q, choice of P, choice of Q is a game, a function that basically takes that trace and turns it into a result, so that actually executes the game. You have a definition of when Q wins, so Q wins if at the end we have classical 1 state. And finally you have a theorem winning if there are Q has choices such that whatever P does, Q wins. And then use Coq to actually prove that. And you can, in this way, prove that yes, Q always has a winning strategy. So this is a very simple example, but this is something that we've actually sort of managed to prove in Coq. When we then go slightly further, and this is where you start seeing that this is not entirely easy. So entanglement in Coq. So the definition is that your quantum state can't be expressed as a tensor product of a smaller state. It means that proving the non-existence of something constructively is pretty hard, because you have to prove that there's no way that you can construct this tensor product. It's always difficult. So we've sort of decided for an alternative definition going by probability. So by measuring something, you change the probabilities of the probability distribution of the rest of the quantum state. And the qubit is entangled if measuring one bit affects probability of the other bit. Proving the equivalence of two notions might be hard, but that's something that we haven't really looked at properly. So that starts looking like this. So if I have an n-qubit vector, means that there are no, so this is the sort of the standard definition. So I can't, so if I have Q1 and Q2, smaller states, so there are no Q1 and Q2 smaller qubit vectors that when tensor together produce Q. The out matrix is, you see that as a type coercion, basically it turns a qubit into a matrix, so that everything, so this is the tensor product, this matrix equivalence, so just turning a qubit into a matrix. So this is the standard definition, and you have here the entangled definition, which is basically, so I've got, again, an n-qubit vector, I've got two bit numbers, which are in that vector, so have to be smaller than n, so you turn them into, so these are two places in my qubit vector, and then I have the possibility, so if I, so I have so you run the outcome of measuring P1 in Q, and then the thing is, so if I measure P1 and then P2, so the probability is different than when I just measure P2. So basically measuring one bit changes the probability distribution of another bit, which is the other definition. And hopefully you'll be able to prove that, so and this is the definition of entangled then, so there are two bits such that I can actually say that these two, so by measuring one I change the other. And then hopefully you'll be able to prove that this is equivalent to this. So if my entangled TP is true, then entangled is true as well. But that's something we haven't actually done yet. So measurement, and this is where sort of corner starts becoming slight problem, because measuring in a qubit state vector, it basically uses division to divide out the parts of the vector that you've measured, so that you've collapsed. And given that it's constructive, you actually need to prove that you need to provide a proof to your operation that you're not dividing by zero. So you need to tell me, yeah, the number we're not dividing with. This is not necessarily true, because we might already have measured before, so there's no guarantee that the probabilities aren't going to be zero to begin with. So then you end up having this kind of horrible axiom saying that, yeah, you know, it's decidable whether any part in my qubit state vector is either zero or not zero, which is slightly dodgy. So it's not really something that it's not really true actually. So this is a bit, and yeah, so this is the constructivity of Korn, and SS reflect, as far as we've seen, doesn't have this problem. So then because then you end up, so the measurement now looks a bit, so because you use this axiom here, basically you do a case distinction. So I measure one bit in my qubit vector, so I is the bit, Q is the qubit vector. If it's zero, then I basically just return exactly what I had before. Now if the probability is zero, it's not going to happen. Otherwise, I check whether my second bit is 0, and then so the second part of the equation, and then sort of, yeah, if that's 0, I again go on to the exact same thing. And then otherwise I can actually do my division, and you can see that here, so my sum 0 GT and sum 1 GT, those are so these are the parts, basically these are the probabilities that the result of my measurement is 0 or the result of my measurement is 1, so I'm measuring a bit. And then you can see that I pass these proofs, some 1 GT and some 0 GT, I pass these proofs on to the function that actually calculates the resulting state vector. So you need those axioms to actually sort of later down the line somewhere say, yes, I am not dividing by 0. So if you have entanglement measurement, you can actually do sort of make a start on quantum interpretation. Is more or less the stage we're in now. So you have a gate with three qubit gate, which is a C0 gate tensor together with the identity. Second gate, Hadamard tensor identity. Then we have so Alice. We used to call this trace, but the thing is, you always got a slight confusion between trace in the process calculus sense and trace in the algebra sense. So we've decided to call this spoor, which is basically the Dutch word for trace. It turns out to be actually an English word as well from the Boer War in South Africa. So it's a really proper term. So Alice basically, what Alice basically does in quantum interpretation is she transforms the first gate and uses the second gate. And then, so that's her particular process. And then the function Alice basically calculates the result of that particular process. We can define Bob. So Bob basically, because Bob, depending on the result of his measurement, basically, so if that's false, then he applies, depending on the result of his measurement, he applies certain gates. So we can see here, either identity, the X gate, the Y gate, the Z gate. And then, okay, slide. And then, if you put all this together, so you have the Coq function Alice, which does basically joins the input qubit Q with the entangled pair, applies the gates to that resulting qubit, and sends the classical bits, so 0, 0, 0, 1, 1, 0, 0, 1, that's exactly what we saw here with the Bob, false, 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 true, true, false, true, true. So it sends those bits depending on the results. Then, depending on the received pair of classical bits, Coq function Bob applies a specific gate, and this happens. And then the idea is that we can prove that Bob's after Alice function preserves phi. So basically, if I use so for all possible phi, there is the other two qubits I can provide. The Bob of the Alice of phi is exactly the same thing as the phi here, and what happens to the Z isn't really relevant at this point. And that's sort of the state we're at now. So, future work. So at this point, we're sort of the first thing is obviously to convert the development properly to SS reflect. So that's using that library. And then the next step is going to be actually to properly represent quantum process, because you can see that here this is all held together with functions. We'd really like to have a proper probabilistic calculus, something resembling Markov chains, to actually look at the proper sort of the process calculus, the probabilities of measuring things, what happens afterwards, depending on the results, you do something. And then, if we've done that, we can properly implement quantum teleportation. And obviously, after that, we can go on to any other protocols we might care to think about. So, yeah, that's it for me, basically.
Any questions, comments? So you start off from very low level quantum mechanics, like very concrete. Are there any plans to start a little bit higher level?
Well, no, so for now, it's not, no.
Yeah.
Does your program let's say, a protocol which takes an arbitrary number of inputs?
Yeah, of course. I mean, that's the whole thing. So yeah, we start on a low level, but obviously, it's basically Coq is a programming language. So you can very well hide all the sort of stuff that's going on down below and start on a very high level. So because that's also what we see in switching from core to SS reflect. The high level definitions aren't actually changing that much at all. It's really the low level stuff that changes. So yeah, that's definitely possible.
You have two definitions of entangled are not equivalent.
Okay, well that's
Take 3 qubits, say 0, 0, 0 plus 1, 0, 1. Then your first definition is false, and your second is true.
Okay, well that's that problem solved anyway. Thanks.
Okay, we thank the speaker again. So we move on to the last